Thank you. Okay, so thank you very much. It's a great honor to be here. And it's actually also a great honor to be in the JDG family. So nowadays, actually, people download mostly articles from the web. But when I started working as a young student, it was still customary that you would actually go into the library and pick up volumes and look actually at the articles on the hard copy. And one of the things that I learned pretty quickly is that there are issues of JDG which are heavily used. In fact, there are certain years of JDG in which, like, you open the book that you have in the library, which collects all the articles, and it's completely wasted. And well, it didn't happen to me with many other journals, in fact. Okay, so the talk that I'm going to give today, it doesn't seem so much related to the topic of the conference, which is differential geometry. But in fact, I will show you there are a lot of relations, and I hope to convince you about this. Unfortunately, I cannot show you the most convincing arguments because that would involve a lot of computations, and I assume this is a kind of general audience which is not too familiar with the topic. Okay, so first of all, up to a few months ago, actually, this was called the Onsager conjecture. So the topic of the talk is that actually this conjecture, which dates to 1949, and it was a conjecture of a famous theoretical physicist, Lars Onsager, has been recently solved. And one of the interesting things is that it has been recently solved by taking some techniques which actually were born in differential geometry for solving another problem. Okay, so first of all, what is it about? So this conjecture that now is a theorem. So it's about the Euler equation. So the Euler equations describe the motion of an incompressible fluid under the idealization that there is no friction between nearby particles, right? So actually, layers of fluid can slide over each other without creating any friction. So the unknowns of these systems of partial differential equations are the pressure, which is a scalar field, and the velocity of the fluid. So the velocity of the fluid is a function v of the position and time. So it is a vector, and it gives you the velocity of the fluid particle, which is sitting at time t in the position x. So x is a space variable, which we will usually take to be in R2 or R3, and t is a time variable, so t will belong to an interval. So the pressure P is a scalar, and it's a little bit more, it's a little bit less intuitive from the physical point of view what it does. So its gradient is actually a force, and you can think about it as a reaction of the fluid to the fact that while the fluid is moving, is maybe trying to occupy the space in a less efficient way compared to the fact that the fluid has to be incompressible. So say particles of fluid maybe try to enter into a certain area where there are other fluids, other particles, these particles are actually reacting. And the gradient of the pressure is this force due to the incompressibility. It's often thought, and there is an interpretation of this, as a Lagrange multiplier to the fact that you are an incompressible fluid. Okay, so this is the system of partial differential equations. So here you see a vector-valued equation, and here you see a scalar equation. So this is actually the incompressibility constraint. So the divergence of the vector field v is equal to 0. And this is, we will see later, the conservation of momentum for the fluid. So now you see that the only nonlinearity in the partial differential equation is this blue term. This is the advective term. So if you write it in components, so this is a vector, it's the divergence of a matrix, and the ith component of this advective term is the sum of the j derivatives of vj times vi. So these are the entries of the matrix V tensor V. But now you see that the fluid is incompressible, so the divergence of V is equal to 0. If you have a smooth solution, then you can pull out this Vj, right? So because dxj Vj is equal to 0. And now you have this expression. So in fact, if you look into the literature, most of the time, this advective term is written in the following way, right? So which reflects actually this computation. So the two ways are completely equivalent when you have smooth solutions. Okay, so in this talk, let us set some notation. We will actually consider solutions over some time interval. And then most of the times we're going to consider solutions which are periodic. So the domain of definition is the periodic torus times the interval. And it's either the 3-dimensional torus or the 2-dimensional torus. Occasionally, actually, we will take that the space domain is the entire 3-dimensional space or the entire 2-dimensional space, which means there is no periodicity assumption. So, but most of the time, we will actually be in the periodic situation. Now, if you look at this interval I might actually assume that I is a bounded interval or a half line. In this case, we will use the convention that the left endpoint of the interval is 0. And if you have such a situation, usually you complement your system of partial differential equations with some boundary condition and initial data in particular. So you assume that the velocity at the initial time is equal to some given velocity v0. Okay? So that's actually like the most natural condition on the fluid. And since it is a classical system of equations in mathematical physics, you expect to be deterministic. So you start with a certain initial data, initial configuration of velocity. The system of partial differential equations should completely determine the evolution of the unknowns of V and P. Okay. So sometimes we will actually assume that the interval is the entire real line. Okay. Then you have the so-called ancient solutions. So they existed for all negative times, and they exist for all positive times. Okay. So now, the Euler equations were derived more than 250 years ago. It's one of the few instances in the physics and mathematics literature in which it seems to be that the thing is attributed really to the person who did it. I don't know of any reference to this system of equations before the paper of Euler. And the paper of Euler actually writes down the equations essentially as we write it down. I mean, there's no cheating in here. Actually, Euler derived the equations under more general conditions. So the equations that we're writing over there are the equations for the incompressible case, right? So, but he also assumes to have a general density rho. So it's just one case of these equations. So there are actually several fundamental and outstanding open questions in this field. So the most famous is whether you have blow-up of solutions, of classical solutions in finite time, in 3 dimensions. So if you are in 2 dimensions and you solve the Cauchy problem with a nice, smooth initial data, there's a solution for all time. But in 3 dimensions, there's a solution for short time, and you don't know whether this is going to create a singularity or not. So if you think about this problem, if you add viscosity, if you put the Laplacian, if you regularize a little bit the equation, you have the Navier-Stokes equations. And in 3 dimensions, the same problem is also open for the Navier-Stokes equation, and it's one of the famous millennium problems, one of the famous Clay-Price problem. So this talk actually is not touching this issue, not that I know of, at least. I don't have anything somehow. If somebody discovers that there is actually a connection between what I'm going to tell you today and the blow-up problem, I mean, I would be happy. But that I know of, there is no connection. Okay, so let me now enter into a little computation that you can do. So if you have a smooth solution, you can scalar multiply the first equation by V. Okay, so you scalar multiply. So here you see the scalar multiplication between V and the time derivative of V. And here you see the scalar multiplication between V and the advective term, and here between V and the gradient of the pressure. So it's a very simple algebra. So you see that here you have Vj dt Vj. So this is the time derivative of Vj squared, and you summing over J. So this is the time derivative of the modulus of V squared divided by 2. You can make a similar computation over here. So you see Vj and dxk Vj. So this is actually the dxk of Vj squared. If you sum over J, you get the modulus of V squared divided by 2. And when you sum over K, you get the V dot grad. And here, of course, you see V dot grad the pressure, right? So this term actually the sum of these two terms can be written in this way. Now, since actually V is divergence free, you can pull out the gradient and write everything as a divergence. So the time derivative of the modulus of V squared divided by 2 plus the divergence of this blue object is equal to 0. So this is nothing but the balance of the kinetic energy written in a local term. So this is the law the local law of conservation of kinetic energy. Now, if you integrate in space, for instance, if you are on a periodic setting, you integrate this guy on the torus, and you get the total kinetic energy, right? So modulus of V squared of x and t divided by 2. But then if you integrate this one in space, and you are, for instance, in a periodic setting, since this is a divergence, actually the integral is equal to 0. So you derive this identity. And this identity tells you that the total kinetic energy of the fluid is preserved along the flow, which is very natural, because you're assuming there is no friction, so you cannot dissipate the kinetic energy by heat, and there is no external force, so the system is isolated. The total kinetic energy is then conserved. Particular, for instance, as a consequence, if you start with the initial data equal to 0, the kinetic energy is identically equal to 0. So there's only one solution, which is just the trivial solution. So if you start at rest, the fluid remains at rest, as somehow it should do if it is a well-behaved fluid. OK, so now let me actually pass to weak solutions, because the conjecture that I'm going to state, this Onsager conjecture, which now is a theorem, actually regards weak solutions. So how do you define actually generalized solutions? And then we will also discuss why would you want to define generalized solutions. So there are several ways, and they actually all turn out to be equivalent. So one possible way is just to say the only nonlinearity in the system of partial differential equations is this V tensor V. If I can define V tensor V, then I have all derivatives outside. So as long as V tensor V is a distribution, everything is well defined. Now, to define what it is V tensor V, you just need the V to be square summable, right? Which is actually a very natural assumption if you think that the energy is exactly the integral of modulus of V squared, right? So an L2 assumption is very natural in this setting. So you assume V is in L2, and then you define solutions in the sense of distributions. Now, another thing that you can do is you can use Fourier series in space. This is a very classical thing in mathematical physics, in the literature of partial differential equations. People have been doing it for a couple of 100 years. So you write actually the function, the vector function V and the pressure P as a sum of Fourier modes, which are evolving in time. So you only make a Fourier transform in space, and you are actually in the periodic setting, so you're writing V as a Fourier series. Now, the unknowns are the Fourier coefficients. So the system of partial differential equations translates into a system of ordinary differential equations. Of course, when you are actually looking at the term V tensor V, that's where actually you're summing over all Fourier coefficients. So you get a series, and you actually, the first thing that you can actually ask yourself is, when is this series summable and well-defined? And it turns out that the series is summable and well-defined when V at each time t is in L2, okay? If V were in L2 of space and time, like in here, then the series would make sense for almost every t somehow. So that's one possible definition then of weak solution. You write it in Fourier series. You have an infinite system of ordinary differential equations. And this infinite system of ordinary differential equations has a well-defined meaning of solution if you assume that V is in L2 for every time. OK, you can actually take another point of view, and that's very natural. So you can take the point of view of continuum physics and just look at what the equation is telling you for the evolution of a fluid element omega, and derive a similar weak formulation. So all of these formulations are actually equivalent. One of the nice things that you can do is look at this continuum physics, because in fact, it's a kind of reverse process compared to what people do, for instance, in the physical literature. So I'm giving you the system of PDEs, and then I'm deriving the local balance of momentum and mass on the fluid element. But in the literature of physics, actually, you do the other way around. So you derive the local balance of momentum and mass for the fluid element, and then from that, you actually write down the systems of equations, assuming that V and P are sufficiently regular. So for instance, conservation of mass means that if I give you a fluid element, there are as many particles entering it as there are particles going out at each time, right? So because the amount of fluid which is in this fluid element is constant. So that simply means that the flux of V on any fluid element omega has to be equal to 0. And this is just this condition. Of course, if you integrate this by parts, it tells you that divergence of V has to be equal to 0 because you integrate over all fluid elements, and the integral of the divergence of V over every omega is equal to 0. The other equation that you can write down is the balance of momentum. So this is telling you how the momentum of the fluid element is changing. So this is the variation of the momentum, and this is due to the particles which are entering and exiting the fluid, and also the action of the force that you know is just the gradient of the pressure. Even this one you can integrate by parts, and if you assume that V and P are C1, then you derive the other vector valued equation for the system for the incompressible Euler system. But then on the other hand, you just look at these two equations, right? And they make perfectly good sense, even if V and P, for instance, are continuous solutions, right? If they are continuous functions, you can write down this guy, and you can write also down this guy. So you might define weak solutions which are continuous as simply functions V and P which are satisfying these balance laws for every fluid element omega that you take, which is a sufficiently smooth domain, for instance, a C1 domain. Okay, so why do we care about weak solutions? So there's something actually interesting going on here if you add a small viscosity. So take the system, take the Euler system and add a small viscosity. So this is just the Navier-Stokes system with a viscosity which is close to 0. Now you can write down the energy conservation law for the system. And of course, if epsilon were equal to 0, this term would not be present, and you have the conservation of the kinetic energy. But if the dissipation is present, actually you have a part over here in which the fact that there is a friction, the fact that there is a viscosity, is actually responsible for the dissipation of the kinetic energy. So now you see here in front there is an epsilon. On the other hand, it's something which is known since the time of Kolmogorov that it is expected that typical solutions of the Euler equations actually dissipate energy independently of this epsilon. In fact, there's even a heuristic law which is kind of derived over here, which is written over here. The dissipation of the energy should be proportional to the energy to the power 3 over 2. But this beta, this coefficient, is independent of this epsilon. At least under some assumptions. I mean, for instance, the fact that you're looking at the flow whose macroscopic scale is somehow fixed, something like 1. Now, if you believe this, you should be able to take epsilon going to 0 and to find sequence of solutions whose dissipation of the kinetic energy stays bounded away from 0. So the epsilon is multiplying the dissipation, right? I mean, the epsilon is multiplying this quantity over here, but nonetheless, this Q of T should remain independent of epsilon because it should be essentially of the size of the kinetic energy to the power 3 over 2. So this, of course, means if it is true, you should find sequence of solutions which certainly are not converging to a classical solutions of the Euler equation, right? So this should happen typically. That is what the theory of turbulence is saying, but somehow the disappointing thing, at least for me, is that you can't actually exhibit a single sequence which is doing this, right? So this should happen typically, but as a mathematician, I would like to show you that it happens at least once. And this is, as far as I know, completely unknown in the literature. So there's not a single example which is rigorously proving that this is actually happening. Okay. So in a famous paper in 1949, which is the topic of this talk, actually Onsager said, wait a minute, let us actually set epsilon equal to 0. If this picture is correct, actually, what it's telling you is that when you go back here, this quadratic term is responsible for most of the dissipation. So it's not, I mean, if you take away this term and you have a kind of classical linear Stokes equation, which looks more or less like a heat equation, of course, the dissipation is proportional to epsilon. But the dissipation is not proportional to epsilon, which means actually that this term is doing much more damage or is wasting much more energy than you would expect. So in particular, you would expect that if that is true, then you can set epsilon equal to 0 and expect the existence of solutions of the Euler equations which dissipate the kinetic energy, even though there is no friction. Okay.
Question about the definition of Q. Does it include the epsilon?
Yeah. Q includes epsilon inside. Yes, Q includes epsilon inside. Yeah, precisely. Okay, so this is the conjecture now. So the conjecture is the following. So there's actually a threshold in the regularity of the velocity v for which you can validate the conservation of of kinetic energy. So if you remember, we made this computation that if v is C1, then the kinetic energy is preserved. And the conjecture is actually that there is an intermediate threshold which distinguishes between two types of behaviors. So if you take a Hölder continuous solution in space, so instead of being C1, you assume that V is Hölder with an exponent alpha, then when alpha is bigger than 1 over 3, the total kinetic energy of V is constant. So you have energy conservation. And if alpha is less than 1/3, then actually there should be weak solutions which waste the kinetic energy, I mean, for which the kinetic energy is not constant. Okay, so this is the conjecture, and you might wonder what is the significance of this exponent 1/3. So this is not a random exponent, but it has to do with the theory of ideal turbulence. So it's a physically meaningful exponent. I'm not going into that, though. So, of course, the solutions that were considered by Onsager are not differentiable, and I mean, he's a physicist. Actually, he got a Nobel Prize in chemistry, and he's actually writing this down in 1949. So you might be wondering whether I'm telling you the true story or whether in his paper he's writing something else. And as often mathematicians do, we are just, translating what the physicist said in our own language. And often during this translation, we actually lose information, or we don't understand them precisely. But it's remarkable. So if you actually go into the paper, he says explicitly, I have to give you a definition of solution to make this conjecture. And he gives a very precise definition of solution. And the very precise definition of solution is via the Fourier series expansion. So it's exactly one of the possibilities for defining weak solutions, which I told you a couple of slides ago. He takes that as a definition. And in fact, if you really look at the paper, you should, if you remember somehow, when you're coming from Navier-Stokes, right, the energy is going down. So it's not only that the energy shouldn't be conserved, but in fact, you're actually expecting that the energy is dissipated, right? So you're expecting the existence of solutions whose kinetic energy is a decreasing function coming from physics. Now, this is somehow, from a point of view of a mathematician, there's though a problem. So the Euler equations are time reversible. So if you only look at the Euler equations anytime that you have a solution which is dissipating energy, you can reverse time by making a coordinate transformation, and you actually get a solution which is energy increasing, okay? But anyway, so he's essentially talking about dissipative solutions. And it's a dissipation which is not induced by the viscosity. So usually in the literature, such type of dissipation is called anomalous. Okay, now the first part of the conjecture, so the fact that if you are above 1/3, the energy is conserved, was proved in 1993 by Constantin et Titi. And actually at the same time, Eying got to the exponent 1/3 slightly earlier, but on a different family of spaces. So not exactly on the Hölder spaces. So Eying was proving something morally very close to the Onsager statement, but the actual statement of Onsager has been proved by Constantin and Titi. And the two proofs are different anyway. Okay, now you might wonder about the other part. So how do you actually construct badly behaved solutions? And here you face a very interesting, for an analyst at least, you face a very interesting dilemma. So if the solution is smooth, it's preserving energy. So you ought to construct singular solutions. So usually, how do you construct singular solutions in the literature? Well, most of the times you actually have explicit solutions which are singular, right? Think about, for instance, Schwarzschild in the theory of general relativity, or a lot of other situations. Now, you might be able to construct solutions nearby a singularity by perturbation methods. Or if you are in the smooth category, you construct solutions by some implicit function theorem, by some iteration, but in that case, you actually land into a realm of smooth solutions, right? So here, there is no explicit solution which is wasting energy for Euler. So there are plenty of singular solutions, but none of the ones that you can write down actually is energy dissipating. They all preserve the energy. And on the other hand, if you run a classical PDE argument to show the existence of solution, for instance, to the initial value problem, you land immediately into the regular situation. So you actually want to create solutions which mess up, but in a non-explicit way, still in a constructive way. So it reminds me a little bit like when people in computer science are creating sort of pseudo-random numbers. They want to create random numbers, but of course there is an algorithm, so they cannot be completely random. It's kind of similar. So you want to actually create something bad. And often creating something bad is actually more difficult than creating something good. Anyway, so there was a first example of a solution which is not energy conservative, and it was constructed by Scheffer back in 1993. So he constructed compactly supported non-zero weak solutions. So solutions which start with the initial data equals 0 if you want, And then they have positive energy at a certain point, and then they have, again, energy 0 at a certain later point. Of course, these are energy non-conservative. This was a very mysterious construction until somehow something like 2006, 2007. There was a different proof in the periodic setting, and this was given by Schnirelmann. And actually, these solutions do not preserve the total kinetic energy, but they have a very rough energy profile, right? So they're just L2 solutions. So it's not clear whether they would have energy which is increasing and decreasing nicely on some intervals. So it was constructed in 2000, a first example of a solution in 3 space dimension which is truly dissipating the energy, so showing that anomalous dissipation is possible. Okay, so in 2007, we actually looked at this problem together with Laszlo Zekelihidi for the first time, and we showed in a very simple way the proof of Scheffer and Schnirelmann. The proofs of Scheffer and Schnirelmann are pretty complicated. So we proved in a very slick way that there are compactly supported non-trivial bounded weak solutions. So not only L2, really L2 of all space-time, but really bounded even. So remember that the Onsager conjecture wants Hölder continuous. So first step is actually to produce continuous solutions. And before that, you might wonder whether you can produce solutions with bounded velocity. These solutions, actually, they can also be prescribed to have nice decreasing energy at a certain point. So they are also displaying anomalous dissipation in a lot of situations. So, okay, as soon as we started doing this, we realized you can actually do much more. So you can prove all sorts of bad behavior for these solutions. For instance, there is essentially no criterion in the literature which can give you uniqueness of weak solutions so far to the Cauchy problem. I mean, every time that there is a criterion coming out, we more or less can use these techniques to give a counterexample. And even with initial data which have fairly mild discontinuities. So this actually was taken up into the literature, and the people discovered that the phenomenon is not only confined to the Euler equation, so the methods that we use to prove this theorem can be extended to several other situations. But let me go on to the important point, though. So what is interesting of our 2007 paper is that Scheffer's theorem and Schnirelmann's theorem look like a kind of isolated singularities in the literature. So nothing looked like the proofs of these theorems. Our proof actually plunges this result into a very long story. So there is a long tradition of counterintuitive examples in differential inclusions and in differential geometry. So what is a differential inclusion? So a differential inclusion is a problem of the following type. You have a set of preferred matrices, which is called K, and you're looking at functions or maps whose differentials take value in this K. So it happens actually in several situations that C1 solutions are not so interesting because they are forced to be affine, because there is some rigidity for several of these sets K. So in these cases, you actually look at Lipschitz solutions, which are differentiable almost everywhere. And instead of imposing this condition for every point, you impose it for almost every point. Let me give you an example of how somehow the proof of our theorem would go if you had a very simple equation. So this is a very simple equation. So you're actually looking at the iconal equation in which you want the modulus of the gradient of a function to be equal to 1. Okay, the plan is to produce a very chaotic solution of this equation. And you produce a very chaotic solution by an inductive procedure. So you start with a smooth map phi 0, which instead of solving the equation, is solving the following inequality. So it's a sort of sub-solutions. And then the scheme is producing a new map phi 1, and then a new map phi 2, and so on and so forth. So along the iteration, you're always a sub-solution. And along the iteration, you improve the distance of the modulus of the gradient to 1 in an L1 sense. So you find actually that the L1 distance to be a solution gets decreased by a factor beta. So this beta is a factor less than 1, which is independent of K. Now, of course, if you have an iteration like this, it means that this integral over here is decaying exponentially to 0. So if you can prove that your phi K is converging to a final map phi, that final map phi, if you converge strongly, will be a solution of the PDE because the integral of 1 minus modulus of gradient phi will be identically equal to 0. But on the other hand, you have the inequality that the modulus of the gradient of phi has to be less or equal than 1 because it will be inherited by this constraint. Okay, of course, there is a challenge here that it is to prove convergence for phi k in a strong sense. So how do you construct, so how do you implement this inductive procedure? So you start with your map phi k, which is smooth, and you want to produce your map phi k plus 1. So look at a small region in your omega and zoom it so that it looks much larger. So now, phi is smooth along the iteration, so it's only at the limit that it will lose regularity. So the gradient of phi, if you take this region to be very small, you can assume it to be almost constant. So here the function will be almost affine by Taylor expansion. Now I have an affine function with slope 1, and I want to improve locally this function without modifying it too much so that the slope is equal to 1. So what I can do is I can actually add a sequence of small perturbations which are zigzag, right? So here the slope is less than 1, but if I do something like this, I can do it with slope 1. But I also want actually a perturbation which is smooth. So what I can do is I can round the edges a little bit, right? But still keeping the steepness of the function close to 1 on most of the domain, okay? Now, of course, if I do something like this, it's a perturbation which is okay in this domain, in this region, but it might not be okay over here because the function is close to be affine here, but with a certain gradient. Here it will be close to some other gradient. So what I want to do is I want to actually cut off this perturbation. So you see, if you write down a formula for the perturbation, it looks like this. So you have 1 over lambda, where lambda is the number of oscillations, times a periodic function computed in lambda x. So now I want to multiply it by a cutoff function so that the perturbation is living only in this tiny small circle. Okay, now when I do that, you can compute the new gradient. So you get the gradient of phi of x. Then you get this addition. So if there were no cutoff function, this addition would actually push your slope to 1. Okay? But there is an error which is called by the fact that you are differentiating the cutoff function. But now, when you are differentiating the cutoff function, you see that there is this red term 1 over lambda, because when you differentiate p, the lambda gets out and cancels with the 1 over lambda. But when you are differentiating c, this 1 over lambda stays here. So you see that you can actually treat this as an error term if you take lambda very large. So if you take lambda very large, you're actually adding a perturbation which is very wavy, and then you kind of cut it off. Now, if you do something like this, right, you can make this improvement much bigger than the error. And one thing that you have to take care of, but this is not too difficult, to actually make this error sufficiently small and make the improvement not too good in such a way that you actually get that the gradient of psi has still slope less than 1. But this is just a technical point. Okay, now you've done that in some region. Now you cover most of your region omega with these joint balls. Of course, in each of these balls, you are oscillating in different directions, and then you multiply by a cutoff. So a simple covering argument is actually giving you this estimate over here. So a simple covering argument is giving you that in an integral sense, the 1 minus modulus of gradient of phi k has become much smaller. Well, much smaller by a factor, which is just some factor less than 1, right? So because in this covering, you're not covering the whole omega, you're covering only some portion. Okay, so once you've done that, of course, you have to bother about the convergence. So that it's actually very easy that phi k is converging to some phi uniformly. That's very easy because, well, you might, for instance, extract a subsequence. You have a uniform Lipschitz bound, right? So you just use Arzelà-Ascoli theorem. But the fact that the gradient of phi k converges to the gradient of phi in L1, so that's not so obvious. And there are, in fact, essentially 2 tools in the literature to do this. One is called Baire category argument, and the other one is called Lipschitz convex integration. So the one is due to several people. So Cellina was maybe the first one in the 80s to notice that there is a very sleek argument that is telling you that more or less any way you perform this iteration, you're converging strongly. But there is a second, which is much more recent, and is due to these 2 authors, Müller and Schwerak, and it's called Lipschitz convex integration. And this one is going to play a major role for us. So the upshot of this is that in all these crazy constructions, in Euler, in the literature of differential inclusion, you've just seen it somehow, the diagonal equation, you're actually constructing a widely oscillating solutions by piling up oscillations at each step. Now, why is actually the Müller and Schwerak paper so important for us? It's because it drew a connection between these techniques and the techniques that people were using in the literature of differential geometry following what is called Gromov's convex integration, so which is a tool to prove what is called H principle results. So I'm not going to tell you what is the H principle, but I'm just going to give you an example. So it's, the key example is called the Nash-Kuiper theorem. So there is an old tradition of counterintuitive constructions in differential geometry. So the Smale's paradox is another example. And rather than actually giving you what is the H principle in general, let me just give you this particular example. So consider a smooth Riemannian manifold MG. And look at an isometry which is mapping M into Rn. So an isometry is a map which preserves the length of curves. So in what follows, we actually deal with C1 maps. And most of the times, you're just thinking that actually this isometry is an embedding. So then these maps are called isometric embeddings. So now I'm not going to give you the Nash-Kuiper theorem. I'm rather going to give you a corollary. And the corollary of the Nash-Kuiper theorem is the following very remarkable fact. Even if you take the standard sphere or the flat square, no matter how small you give me this parameter epsilon, I will be able to isometrically embed it into a very small ball, into a three-dimensional ball, which is of radius epsilon. So now, if you think about it, it's actually a very surprising theorem. And the reason why it's surprising is the following. So first of all, if you ask a little bit more regularity, so if you have actually C2 regularity, there is a classical result by Cohn-Vossen and Herglotz, which is telling you that you cannot squeeze the sphere into a ball of radius epsilon. So the theorem of Cohn-Vossen and Herglotz tells you that if you have a C2 isometric immersion in R3 of the standard sphere, you only can do it by picking up the boundary of the unit ball. So you certainly cannot squeeze it into a ball of radius epsilon. But of course, you can even just make the following practical experiment, right? So a flat square, it's very easy to produce. So a flat square is just a piece of paper. And when you want actually to put a flat square in a very small ball, so one thing that you would like to do is to put the flat square in your pocket. Now, it's very easy to reduce the size of the flat square with an isometric embedding in one direction. For instance, I can do a cylinder like that. But if I want to put it in a small ball, I have to reduce also the size in this direction. And it seems impossible to do it without creating a singularity. I mean, of course, I can do this, right? But if I do this, my map is not C1 anymore. It's going to be a Lipschitz map. Of course, creating a Lipschitz isometric embedding in a ball of radius epsilon is very easy. So now, what does this have to do with our problem? Well, the isometric embedding problem is actually a typical differential inclusion. So when you write down in coordinates the system of PDEs for the isometric embedding problem, you find this system of PDE. So du transpose times du is equal to G, where G is the metric tensor. So here's what actually, at the time when we were studying this problem in 2007, here's what actually was for us a very striking similarity. So you have this situation in the isometric embedding problem. If you have a C1 isometric immersion, you can actually mess it up. But if you have a C2 isometric immersion, that behaves in a rigid way. For instance, you have the Cohn-Vossen theorem. Now, back in the 50s and 60s, Borisov, a Russian mathematician, actually claimed that if you look at C1 alpha isometric embeddings and alpha is small enough, you're able to replicate the Nash-Kuiper phenomenon. So you don't need C1. I mean, C1 is OK, but you can even allow somehow kind of more regularity. And it's interesting, so then we revisited this theorem by Borisov with Sergio Conti and Laszlo. And actually, recently, we got the best exponent for two-dimensional disks. So this alpha for two-dimensional disks can be almost 1 over 5. Borisov actually at the same time also proved the following rigidity version, the rigidity theorem of Cohn-Vossen. So if you take C1 alpha and you let actually alpha be large enough, the explicit exponent is 2 over 3, then actually you have the rigidity of the C2 map. So when we looked at this, we had the following formal analogy. So we had a proof of the Scheffer-Schneiderman theorem, which was a kind of H principle statement. And then we had the Onsager conjecture, which is this threshold between C0, C1 solutions. And then we had this cousin of the differential inclusion problem, which is the isometric embedding, in which you have a similar phenomenon, with a lot of pieces actually missing into the puzzle. So for instance, in the isometric embedding problem, there is no threshold, which actually is coming from physics. And people believe the threshold to be 1/2. So for instance, a Gromov conjectures that the threshold for distinguishing between these two behaviors actually should be 1/2. So now, the Nash-Kuiper theorem is actually a much more general result. So, I mean, there is a theorem which is telling you if you have a short isometric embedding or a short immersion, I'm not going to tell you what this is some kind of subsolution, like we had a subsolution for the iconal equation. So if you take a short isometric embedding, you can actually approximate it uniformly with C1 isometric embeddings. So in 2007, we had a similar H-principle statement for the Euler equation. So if you have a certain notion of subsolution to the Euler equation, you can actually approximate it with actual solutions. So there is a remarkable analogy, formal analogy between the two theorems. Okay, so that actually pushed us into the direction that maybe you can interpret the Onsager conjecture in the lower scale of exponents between 0 and 1/3 as a manifestation of this H-principle for the Euler equations. So that was what actually we started believing. But there is a very big caveat. So when you're actually looking at the literature of differential inclusions, you produce Lipschitz solutions. Or as it is actually for our case in the Euler equations, you produce L-infinity solutions. In the literature of differential geometry, you actually produce usually C0 solutions. And C0 solutions or C1 solutions are much harder. So in the isometric embedding problem, if you want to produce a Lipschitz map, which is crampling the paper, right? I mean, that's a triviality. But if you want to produce a C1 map, then you need the genius of Nash to realize that that is possible. So, okay, it took us quite some time, but a few years later, we were actually able to prove the existence of continuous solutions of the Euler equations which dissipate the kinetic energy. Particularly, we were actually able to prove that there are continuous solutions of the Euler equation which picks energy, any energy profile. So you give me the energy function that you want, and I will be able to produce a solution of the Euler equation which is continuous and picks up this energy profile. Now, the construction is similar to the one of Nash, but it's the first kind of construction that we know of in which there is really a lot of analysis of PDEs entering. I mean, if you want, there is something like this happening. So in the paper of Nash, you can do a lot of computations explicitly. So for instance, this perturbation that you're doing in your iteration is something that you can write down explicitly with a formula. In our case, you cannot do this. You actually have to solve a certain given partial differential equation. And so it's, in a sense, the first time that this type of techniques, instead of being created ad hoc, they're actually created with a machinery which is relating it to some other PDE's problem. And in fact, they're very flexible. Also, from the point of view of convex integration, you can think about this iteration by integrating some more complicated elliptic operators. So the usual convex integration constructions in differential geometry, they integrate simple operators like this. In our case, we actually integrate the Laplacian and the bi-Laplacian. Okay, so of course we had this experience with Borisov, that as soon as you get C0 solutions lead you to the expectation that you can actually compute C alpha solutions. And in fact, immediately after, we discovered that the method is sufficiently flexible to reach the exponent 1/10, which is surprisingly close to 1/3, in fact. So you're not off by a large amount, right? So our expectation at the beginning was that maybe we get some exponent, but the exponent is going to be, I don't know, something which is maybe only theoretical, a small epsilon, or maybe something that if you want to make explicit, it's going to have a very ugly number, like 1/10 to some power. In fact, we got 1/10 essentially with a very crude construction. Now, this has been picked up in the literature again. I mean, there are a lot of further work in which you're handling problems which are related, like non-uniqueness. You can do constructions in 2-dimensional. And again, you can actually use this construction for different equations, because as I told you, it's actually giving you a kind of PDE approach to apply these convex integration methods, or to check whether these convex integration methods might be possible, at least. Okay, so now, of course, the game of the final part of the talk is why can you improve this exponent 1 over 10 to 1 over 3? So let me give you just a little upshot to what the iteration is doing. So the iteration in our construction is solving, so you're thinking of having a sequence of approximate solutions to the Euler equation. So here you see the Euler equations. But there is an error term. So the iteration is inductively making this error term smaller and smaller. So this tensor R circle Q, which is a symmetric traceless tensor, measures the distance of the approximate solutions to a true solution of Euler. And as it was happening in the iteration for the iconal equation, as you go on with Q, you actually make this error, so you make the distance to being a true solution of the Euler equation smaller and smaller. So how do you actually correct VQ, PQ? So you're adding a lot of oscillations. That's one first thing. And these oscillations are stationary solutions of Euler. They are called actually Beltrami flows. And they have slowly varying coefficients. So you have to think about something which is varying very fast. I mean, there is a very fast variable, and you're feeding actually a lot of oscillation to this very fast variable. But then there is another slow variable which is changing, for instance, the direction of the oscillation slowly in your domain. So if you remember this picture in which we had all these circles, right, with a lot of oscillations in all of the circles, the huge problem in this construction is that I cannot use cutoffs, and I cannot simply make perturbations in separate circles. Because I want a construction which is actually giving me a uniform convergence. So I have to modify the solution everywhere. So where I was actually putting the cutoff, now I have to face a very important problem. That is, I have to make these circles talk to each other. So that was a very simple trick which works in the L infinity situation, but that is not going to work here. And in fact, there's even a bigger problem. That is, these perturbations that we are adding are static, but the equation is actually evolutional. So what we're actually doing is that the perturbation in the step VQ is also transported along the flow of VQ. So it's a pretty complicated construction. And along these complicated constructions, there are a lot of error terms compared to what I showed you on the iconal equation, in which there was one single error term. And somehow the name of the game is that you want to optimize all these error terms in such a way to have the best possible convergence and then reach this exponent 1 over 3. Okay, so now, so here it was a major thing which happened for us, and is that Phil Isett got his PhD and entered into this business. And his first contribution was to actually improve our exponent from 1 over 10 to 1 over 5. Okay? He did it by showing that there is a non-trivial compactly supported solution. So it's energy non-conservative, but it's not making this anomalous dissipation, right? So our theorem is slightly stronger because it allows you to prescribe the kinetic energy. So what were his ideas? Well, he has a better approximate transport. So I told you that I have to deal with all these dots. And I cannot deal with all these dots by simply making them sort of separately in the perturbation. So we use actually a partition of unity in our paper in 2011, right? So he's using a much better algorithm for transporting. And instead of having a partition of unity in space and time, he has a partition of unity only in time. So it's as if he's able to make the perturbations on stripes, on space-time stripes. So instead of having a lot of dots, he has a lot of slabs. And this makes a tremendous improvement on the estimates. Well, he actually also has more careful estimates. Okay, so slightly after, together with Tristan Buxmaster, we noticed that you can get the same Hölder exponent, but with a shorter proof. And in fact, if you optimize on his proof, you get also the anomalous dissipation, which is, as I told you, relevant from the point of view of the paper of Onsager. Okay, so then we were actually able to reach the threshold 1 over 3, but not in the statement of the Onsager conjecture. So Tristan noticed that it's possible to keep this 1 over 5 exponent, but make the regularity of the function v better at most of the times. And after a lot of work, in 2014, we actually made this quantitative, and we proved that there are non-trivial compactly supported solutions of the Euler equations, where the space regularity is the critical one, is the one of Onsager, but you cannot really say that there is a uniform Hölder estimate because the Hölder estimate is depending on the time where you are, and in the Onsager conjecture, this function of time would be L infinity, whereas we are only able to prove that it is L1. Okay? Then two things happened in the last year. So first of all, Laszlo and Sara Daneri had a very clever idea to replace the static perturbations, which are Beltrami flows, with another family of stationary solutions. And this was because they were interested in proving a true H-principal statement. So Laszlo got interesting in the question. In the L infinity category, we have an H-principal statement which is telling you we can start from any subsolution and we can produce a solution nearby. But in C0 category, we actually lacked such a strong statement. He and Sara used actually this modification to prove an H-principal of which the anomalous dissipation is a manifestation, but he wasn't able to improve the exponent over here. Now, one interesting fact is that actually this statement is not possible in dimension 2, but I don't have time to tell you why. So let us skip actually to the last two slides. So then Phil Isett again actually was able to take this improvement by Sara and Laszlo and add another key additional idea. So if you remember, in the constructions, we have this partition of unity, and one of the things which was bothering Laszlo and Sara is that when you have this partition of unity, you actually have overlapping regions in which the estimates go pretty badly. So Phil had a fantastic idea, which was the following. So before actually making this improvement step, he makes, so the whole problem of the partition of unity is to actually improve on this error, right? So he actually has this idea that at each step, it's possible to make this error supported on small time slabs in such a way that the correction that you have to add can be really made separated without having actually any partition of unity. And how does he do that? He alternates the solution that he has with exact solutions of the Euler equation. And the remarkable fact, which was actually proved before, is that you can do that. I mean, you can solve the Euler equations only because you know the well-posedness of the Euler equation, so you can solve it with smooth solution only for a certain amount of time. But the existence time that the classical theory gives you gives a size for the slabs which is exactly compatible with the scaling of the Onsager conjecture. And okay, so actually this remark that the well-posedness theory is compatible with the Onsager scaling is present in the previous papers that we had on the problem, but we were not able to exploit it. Okay, so final touch. Just this year, together with Tristan Bookmaster and Vlad Vikol, we actually improved Phil's proof that, as you see, has compactly supported solutions to actually give an H-principal statement, as in the Daneri-Zekeli-Hidi paper, and the H-principal statement has the effect that you can actually show anomalous dissipation as a corollary. So it's possible in the Onsager critical exponent to improve Phil's proof to actually prove that there are solutions which are truly dissipating the energy, which was in a sense missing. I mean, the only thing which was missing in his paper from the point of view of the Onsager statement. Okay, so sorry for going a little bit extra time. That's actually the end of my talk.
So if you consider these solutions, then are there any extra conditions you expect that limit of this Navier-Stokes equations with epsilon small?
That would be a wonderful result, which we would very much like to prove, but that we don't know how to prove. So as soon as we add viscosity, it gets problematic. Now, what is, I would say, almost 100% sure, because I have some computations and so some partial results, is if you add a viscosity which is not too strong. So if instead of adding the Laplacian, you had something milder than the Laplacian, then it's possible to make this iteration with some viscosity. But then the Laplacian is actually so mild that it doesn't give you all the features of the Navier-Stokes equations, like, I don't know, partial regularity and so on. So yeah, it's possible to do something with viscosity, but coming to the initial question of producing actually a sequence of solutions to the Navier-Stokes equations which displays this anomalous dissipation, that is actually a large open problem. It's maybe the most interesting actually open problem in this business. Right. So weak solutions are actually solutions which are respecting the balance of mass and the balance of momentum in this fluid element formulation. Of course, what this construction is telling you is that when you have enough smoothness, and you don't need that much smoothness as you would imagine by calculus 1, calculus 2 computations. When you have enough smoothness, you're also able to derive from them the balance of energy, right? So I give you the fluid element, and you compute the amount of energy by computing the flux, which is coming from this blue term, if you want, back into the slides. So what this construction is telling you is that if you only assume the balance of mass and momentum, and you don't assume enough regularity, then you cannot derive the balance of energy in this sense. So that's one upshot. But the weak solutions, the answer is they conserve the balance of mass and balance of momentum in an integral sense instead of a differential sense. Sorry? Yeah. Okay, so what actually happens in our construction is that these solutions are badly behaved from time 0. Okay, in the classical situation where you have a nice initial data. The nice initial data actually gives you a nice solution up to a certain time, and you don't know whether this creates a singularity or not. So since we don't know whether this creates a singularity or not, we don't know whether we can apply. I mean, if you were able to create a singularity, probably right after I would be able to do a construction like this. So for instance, in other systems of equations, in compressible fluid dynamics, where you know that there is a shock wave that can be created, we can start from a smooth initial data, wait until the blow-up time, and from the blow-up time, you can actually start this mess. But this can only start if the initial data is sufficiently rough. So that's why we cannot touch the blow-up problem.